Oh yeah. Catchy, isn't it? Good morning, good afternoon, good evening, whatever the case may be. We are back and better than ever for part 2 of probability. Let's get right to it, shall we? Theoretical. How about theoretical probability? This is the probability that you are most familiar with. Exactly. Theoretical probability is given by the probability of an event A, or the number is equal to the number of members of the event A over the total number of possible outcomes. So it's the number of favorable outcomes, what we're looking for, over the total possible number of outcomes, or the universal set, which we talked about earlier. And this is how it looks like, this is what it looks like on your formula sheet. So let's get to some examples right away. A ticket is randomly selected from a basket containing 3 green, 4 yellow, and 5 blue tickets. I'm going to go ahead and total that right away. That's 5 plus 4 is 9 plus 3 is 12. Determine the probability of getting a green ticket. So the probability of green is equal to the number of greens, which is 3 out of 12, which, please simplify, folks, is 1 out of 4. We could also write that as a decimal, 0.25. We can also write it as a percent, however you want, whatever floats your boat. Fraction is fine. Part B. A green or yellow ticket, so probability, that looks like a 6, I'm going to do better this time, of green. How about, look at that G, huh? Look at that G. Or yellow is equal to the sum of those two. So green or yellow would be 3 plus 4 over 12, which is equal to 7 over 12. You like apples? I like apples. How about them apples? C, an orange ticket. Orange, let's see, green, yellow, blue. Oh no! Probability of orange, there aren't any orange. That equals 0 out of 12, or 0. Very simple, easy peasy. D, green, yellow, or blue ticket. Well, that's all of them, isn't it? That's 12 out of 12, which equals 1. In fact, it is certain that someone will draw a green, yellow, or blue ticket. Events which have no chance of occurring, or probability 0, or are certain to occur, or probability 1, are two extremes. Okay? So for any event, the probability will lie between 0 and 1, including 0 and 1. So let's take a look at a couple things here. An ordinary 6-sided die is rolled once. Determine the chance of getting a 6. Well, that's easy. There's only one 6 on there, so that, and 6 total outcomes, so that's 1 out of 6. Not getting a 6, well, that would be 1, 2, 3, 4, 5, wouldn't it? So that would be 5 out of 6. Getting a 1 or a 2, well, that would be 2 out of 6, which is equal to 1 out of 3. Not getting a 1 or a 2, well, that would be 4 out of 6, which equals 2 out of 3. Okay? And what's behind this mystery box down here? Let's take a look, shall we? All this is saying, or all it's talking about, is complementary events. In example 5, that was this example here, notice that the probability of 6 plus the probability of not 6 is equal to 1. And that the probability of 1 or 2 plus the probability of not 1 or 2 is also equal to 1. These are called complementary events. Backing up here, 1/6 plus 5/6 is 1, and 1/3 plus 2/3 is 1. Two events are complementary if exactly one of the events must occur. If A is an event, then A prime, or its complement, is the complementary event of A, or not A. So we have A and not A. So the probability of A plus the probability of not A is always going to be equal to 1. That can be helpful. Sometimes it's useful or helpful to use grids like we did before to help us find probabilities. So let's do this, shall we? Use a two-dimensional. Now this is an easy example, but when you get more difficult ones, sometimes a grid is a good strategy. I just want to put it out there for you in case you do want to use it. Use a two-dimensional grid to illustrate the sample space for tossing a coin and rolling a die simultaneously. Then we'll get into this, but let's first make the grid. So we're tossing a coin, doing two things, and we are rolling a die. So this is, I'll put the die right here, and I'll say, let's see, 1, 2, 3, 4, 5, 6, and we're tossing a coin, so that would be heads or tails. Remember how we did this in the previous video? Then we would make lines here, horizontal here, representing all the tails, and here's for heads, and then we're going to put a vertical line for each of the 6 numbers on the die. So this is 1 and 2, and don't you wish you could draw as well as I bet you do. Or as well as me, I suppose is the right way to say that. So the intersections represent all of the possible outcomes. Yes? Say yes? Yes, so each of these points here, this would be heads 1, this would be tails 1. Oops, I almost made another H. Heads 2, tails 2. Heads 3, tails 3. Heads 4, tails 4. Heads 5, tails 5, you get the idea. And heads 6, tails 6. It's a nice little tool to have. What's the probability of tossing a head? Well, I mean, that's really simple. We have 12 outcomes. All of these are heads. That's 6 of them. So that would be 6 out of 12 or 1/2. Getting a tail and a 5. Well, there's only one tail 5 combination. That's right here, right? So that would be 1 out of 12. Getting a tail or a 5. Well, that would be all of these, because you can get a tail or you can get a 5, yes? So these are all tails, but this counts as well because there's a 5 here, since it's an or. It doesn't have to be both, it's just or. So this is 6, 7. This is 7 out of 12 would be our probability. Okay, and last but certainly not least, tables of outcomes. People exiting a new ride at a theme park were asked whether they liked or disliked the ride. The results are shown in the table alongside. Use this table to estimate the probability that a randomly selected person who went on the ride liked the ride. Well, we are going to need some totals here, so I think we should probably fill in the totals, maybe extend our table a little bit here, and also along here will be helpful as well. And let's see, 55 plus 28 is 83. 17 plus 30 is 47. Then adding down 28 and 30 is 58. And then 55 and 17 is 72. So that's going to help us out here. Let's see. And okay. And what both of these should add up to vertically and horizontally for a total of 130 people. Okay. All right. And this is a total too as well, obviously. Okay. Use this table to estimate the probability that a randomly selected person who went on the ride liked the ride. Well, 83 people liked the ride, and that is 83 out of 100, which is about 0.638. You don't have to do the decimal. I'm just doing it because I happen to know it. B is a child and disliked the ride. So that would be right here, child disliked. That is only 17. So that's 17. Oops, why did I put 100 here? This should be 130. Thanks for catching that. That was Mrs. Becker's fault. So that would be 17 out of 130. Part C is an adult or disliked the ride. Is an adult. Well, how many adults do we have? Well, we have 58 adults, 28 plus 30, or disliked the ride. Well, we already have the 30 who disliked it, so we would just have to add this 17 right here. So it's 28 plus 30 plus 17, all out of 130. Okay, and that is equal to 75 out of 130. That's the probability there. D, like the ride, given that he or she is a child. Okay, so we know it's a child and we know they like the ride, so that's this number right here. It's only the 55. But the denominator is going to change. Okay, the denominator is going to be 72 because we are given that the person is a child, and the number of children we had is 72, so that excludes all the adults, so that would be 55 out of a 72. Out of 72. Then the last one is an adult given that he or she disliked the ride. Well, that's kind of weird. Okay. So first of all we know, the group that we are looking at are the ones who disliked the ride. So there was only 47 of them. So this is going to be out of 47. Okay. And then how many of those disliked the ride that were adults? And that would be 30. Okay. So sometimes a table can be very, very helpful. That is it. That is all I've got. Let's see what's on the tunes to take us out. Oh, The Sting, The Police, Every Breath You Take. All right. Hope you enjoyed it. I am... Oh!